Hi, if you are watching this video, it's probably because you are attending the workshop of design and manufacturing of a sample here in Frenetic. The idea will be that we are going to do a small flyback transformer design, and then we will have the material in the lab where will be able to build it and measure it. So let's start. I'm going to share my screen. What we are going to do is start a new design in Frenetic Online. We're going to call it Flyback Workshop. Yeah. And now we are going to build step by step the transformer. So the specification of our flyback is that we want to have 160 micro of magnetizing inductance, is switching at 150 kilohertz. The input voltage is the DC line voltage at the lowest AC line. So the line is 90 volts. So here we have 120 volts, and the output power is 65 watts. The turns ratio is 6, and the output voltage is 20. And again, the output power is 65 watts. So here we have the waveforms, both in the primary side and the secondary side. What we are going to do is first select what is the core that fits better in our transformer. So we're going to first go to the core optimizer, and we are going to check different families of cores. So because this is a flyback, we want it to be, let's say, close to, let's say, the maximum field that the ferrite can withstand, which is 300 millitesla. And we are going to pick up a material rated for 150 kilohertz. The Hertz Q3C95 should be, let's say, more than enough or more than good for this power level. So here, what we can see is how is the performance for the different RM core family. So for the biggest one, RM14, we will have a very low power density. So this component is pretty, let's say, big for this power. And then if we go to the right side, it's the other way around. So we have a very high power density for such a small power. Before deciding which core to select, I'm going to check other cores. Like, for instance, if we take PQ cores, or if we take EFD cores, for instance, let's check and compare all of them. And now we are going to pick up one. So here we have a comparison between all the cores. So basically, I know that I should be moving here around 5 to 10 kilowatt per liter would be a good number for this natural convection transformer. And in this case, we are going to move forward with an RM8 core. Now, what turns to select? We are going to go to the next plot, which is core losses versus number of turns, and we are going to pick up this RM8 core that I was commenting. And here, what we can see is the evolution of the losses with the number of turns. So the turns ratio that we have is 6. So if we want to have a, let's say, good ratio, we should either do 4 times 6, which is 24 turns, or we should either do 3 times 6, which is 18 turns. So if we do 18, it's going to be already, let's say, bigger than 300 millitesla, the flux. So we should go for 24 turns in the primary side. Now we click on apply, and what will happen is that the core section is going to be automatically loaded. Here we will have our 24 turns. The gap is going to be in the center leg of 0.28 millimeters. We have a core loss of 0.42 watts. Now we need to build up the winding. What we are going to do is we are going to use wires that we have in Frenetic Lab stock. So we are going to use for the primary side, for this flyback, we're going to use an enamel wire, okay, with a strand diameter of 0.5. This is going to take 2 layers. And then in the secondary side, we're going to use a triple insulated wire so we can ensure the isolation between the primary and the secondary side. And in this case, because this is low frequency, we're going to choose a 0.1 strand diameter. Then the wire that we have in stock, which is 120 strands, triple insulated wire. Because this is a flyback and we want to, let's say, minimize the leakage inductance, we're going to use a PSP winding arrangement. So we click on Run, and let's check how it's going to be the performance of our flyback with this winding arrangement. I have selected enamel wires, so we can build this, let's say, sample with 2 different type of wires. However, if we were to optimize this transformer further, we could even use lead wire, although it's not really needed, because since as you see here, we are getting a pretty good efficiency and good temperature rise with an enamel wire, which is going to be cheaper than lead wire. Now we can go to the mechanical section, and we can define what is going to be the pins that we are going to use. So we are going to start in pin 1, and we are going to use a pin for a tap. Okay, so if you see here, we have 24 turns in 2 layers. So this means that here, this first layer, we need to cut the wire, go to a pin that we are going to use for connection, and then this third layer, we will start from that pin, and we will finish in another pin. So here we will define that 3 to 5. So 3 is going to be the tap pin, and 5 is going to be the end of the winding. For the secondary side, we are going to use flying leads, which is going to be A and B, and we will leave 20 millimeters of thin copper. And then here we have a summary of our component, and at the bottom side you can see what are going to be the validation measurements that we are going to take over a sample during this workshop. And that's it. If you have any doubt, well, let's save this. If you have any doubt, just came to talk to me. We will try to solve it together.